Joe. Thank you for inviting me.
Yeah. Hello, everyone. Welcome to this week's Quant Seminar. Our first speaker is Professor Tariq Alkhalifa from KAUST in Saudi Arabia. He is currently a professor in the Physical Sciences and Engineering Division. Before joining KAUST in 2009, Professor Alkhalifa was a research professor and director of the Oil and Gas Research Institute at the King Abdulaziz City for Science and Technology. And before that, he served as a postdoctoral researcher for the Stanford Exploration Project at Stanford University. Professor's research interests are in imaging and velocity model building for exploring seismic data with special emphasis on media that exhibit anisotropic behavior of wave propagation. He's also interested in seismic acquisition and processing of near-surface data for better near-surface treatment. Welcome, Professor. You may want to start the presentation. Okay, you can share. I think you're able to share as well.
Great. Let me do that. Okay, got everything here, and let me make this full screen, and hopefully we're there. Okay, it looks okay?
Yeah.
Good. Let me first warn everybody. I had to travel to Italy, therefore I arrived yesterday in Milan at a short notice because ENI, this morning I met with them, want to join our consortium, and we're meeting up to deal with this. Therefore, if anything happens to the internet, I'm hoping this hotel internet will keep up. Otherwise, I hope everything will be fine. I want to thank you guys for having me in this very interesting and prestigious gathering on a topic we definitely like, which is physics-informed neural network. And I thank George for inviting me and everybody for setting this up. What I'm going to talk about is our experience with physics-informed neural network. And a lot of it began in 2019 when Umair came and visited us at KAUST and showed us this potential of physics-informed neural network, and we haven't stopped since then. Therefore, I'm going to talk a little bit about what we have done in that arena. But prior to this, let me give the credit to my group, because the work I'm going to show is my group's work. And let me start by explaining the group and where we come from. Therefore, we're called the Seismic Wave Analysis Group, SWAG. We're focused, of course, on seismic imaging, waveform inversion. I'll mention or explain some of that. And now we're trying to utilize machine learning. Recently, a colleague of mine, Matteo Ravasi, and myself, we started a consortium called Deep Wave. It is focused on machine learning solutions for our problems in exploration, seismic imaging and inversion. And this consortium up to now has 9 sponsors. Not the best in terms of their image. It's like Exxon, Chevron, PGS, not the climate lover type, but we have to do what we have to do, and they have joined us just to access our machine learning tools that we provide. We have a GitHub that all of this will be provided to them as part of them joining and funding our consortium. This is my group. Matteo has his group, and we joined together in the consortium. And you could notice there's a list of different applications within machine learning, whether it's regular CNN denoising, diffusion models for as prior or constraining waveform inversion, and many other applications. 2 of my PhD students, and this is what I'm going to share here, mostly their work, Xinquan Hong on pins for wave fields, and Hashim Tawfiq on pins, mostly utilizing the Icon equation. However, I'm not going to focus on the application more than focus on our experience on dealing with all of this. And we all are part of KAUST. This is a picture from KAUST. George visited us a couple of months ago. I had the privilege of having lunch with him, and he was here, and therefore you could see the different buildings. We're on the Red Sea, north of Jeddah. My office is in this building here, but it's in the other side. It's not toward the Red Sea. I don't have this beautiful view. I have a view of the people that go to have dinner underneath here. But that's fine. That's actually allows me to work more. You could see the numbers here. We have a community of 7,600, 110 plus nationalities, very international university in all terms. We're a graduate-only university focused on research. This is the male-female ratio. We want to improve on that, but for a graduate school, this is not bad. And here's other numbers you could see. Therefore, this is a short description of the university. The scope of what we do in our group is we're focused on seismic waves. We're focused on it to solve a problem globally. For the Earth, I'll show examples. Locally, that means the near surface, trying to image that part, monitor the Earth, but most of our applications are related to exploration, where a lot of our funders tend to fund our projects for these applications. This is actually a picture that was drawn from one of my students who is now working in Shearwaters, that did this very beautiful graph of our scope. And the key words, we are focused on seismic waves. Not much different. They have the same physics as electromagnetic waves or any type of waves that propagate. And what we do is, of course, ignite waves inside the Earth and record whatever scattering reflections we could record on the surface of the Earth. This is similar to ultrasound, similar to medical imaging with many of the tools they utilize. The difference is we deal with the wavelengths that tend to be much smaller or much shorter compared to the medium we deal with respect to medical imaging. We also have a very complex medium that we deal with. Therefore, heterogeneity is very strong. You could imagine, even if you dig the Earth a little bit, you could see how heterogeneous the Earth is. Seismic waves are beautiful. I mean, they could penetrate, if there's enough energy, they could penetrate to the center of the Earth, tell us that the inner core is fluid, the outer core, and come back to the Earth. Therefore, many of the information we know about the Earth comes from seismic waves. And we try to invert it. We apply seismic tomography, seismic waveform inversion, and so forth. And these are the key things we do. Here's a simple example of something very popular in our field. We could assume the one on the left is our recorded data fixed from the field. This is one shot gather. We have a shot where the energy arrives early here, and you could see that the move out takes place as we go further, and we have our receivers or our sensors listening on the Earth's surface. And this is an example of the Earth. This is a slice. Here, the vertical axis is depth, and the horizontal axis is distance. Therefore, we try as much as possible to model. We start from a poor model, then we iterate. It's a highly nonlinear problem, considering the complexity of the model we're dealing with. And we try to approach to a credible velocity model that matches the data. This is the kind of things we work with, whether it's 1D, 2D as a slice, or 3D for this salt body. And you could see an example pointing to something within this complex salt that is resembling the true model. And this is a synthetic model, but it shows the capabilities of some of the waveform inversion. Okay, this is just a taste of what we try to do. And there's many examples. And of course, one thing we have done well as a group is we have won the university hackathon. The university It's an NVIDIA-sponsored hackathon. They do it once a year. Many teams from biotechnology, from other nanotechnology, they join. Most of them work on the computing applications, join to compete. And it turns out, of course, we didn't have 2021 was canceled. We know why. We won 4 out of the last 7 hackathons. Some students from my group. I didn't have anything to do with it. And since we did that, I said to myself, wow, we might be good. I mean, since we're good with GPUs, maybe machine learning is a good idea. And we started 2016 with our first machine learning applications we're trying to utilize. This is what we do the most in helping us solve problems in trying to discover the Earth and trying to image the seismic data. Therefore, the only thing I did to this graph is I added the neural network in the middle here. This is the kind probably George would like, since it's a MLP, which falls under the banner of pins, or what we use with pins. But this is what I added, the only thing I made change to the scope. And we started to develop a philosophy with machine learning. Of course, this is some of the basic knowledge on the topic. Machine learning is considered a predictive model. And this saying really touches on it. The future influences the present just as much as the past. Therefore, our expectations, what we think will happen, affects our decisions as much as what we experience in the past. And this is true. This is how we deal with machine learning, because we have expectations that we try to see if we could predict those, or we could guide the prediction toward those. Therefore, back in the 1600s, a German scientist, Kepler, and others, Galileo and others, tend to develop something we call use the data to predict, for example, the planet motion, the path or trajectory of planets by just following. This is a predictive model. Then came Newton and others and developed physical laws that guided all of this, and we didn't need data to predict anymore, to a point. And for some reason, we took a full 180 and we're back to predictive models. Therefore, this is a full turn. Why? Well, it turns out that efficiency is a big factor. It turns out that there's many problems we cannot solve with our science knowledge. However, the solution is in the balance, and many have really iterated this component. We have imperfect data, and we have limited knowledge. And if we combine the two, I think we could solve many problems. Therefore, in our group, we have a very interesting makeup of machine learning. Of course, we have it as an optimization problem or optimization framework, which it is. And the main guidance to this optimization is, of course, the data. However, we want to include the physics, and pins is a big part of it. We want to incorporate our expectations of the subsurface. Therefore, our prior knowledge, we want to incorporate it in the neural network. We have done so, diffusion models, generative models, we have included in our version in many applications, therefore and we want to take into consideration the neural model inductive bias, because every neural network has its own. We're using now transformers for seismic processing for a special reason, and that's something we wanted to deal with. Therefore, all of this are components to improve our prediction of whatever we need to predict. Therefore, let me go to what we have focused on, and this is a passion of mine. There's 2 subjects that I'm really focused on. Domain adaptation, which is very important in our field because we want to train on synthetic data and apply to real data. This is important to the companies that support us. And we have done many things on this, MReal and Store Seismic, and we have published on this. The other thing is physics-informed neural network, which hits a very delicate, because I like physics, and therefore this is exactly something that is worthy of trying or exploring. I'm not gonna preach to the choir. You guys know about it. I'm gonna just mention we're focused on wave fields, or the high frequency asymptotic approximation, what could be considered as a class of level set, which is the iconal equation, which maps the wave fronts or the singularity of these waves, which are also the geometrical shape of these wave fields are very important as well in many of our applications. And these are the two fields we tend to focus on in using pins. Therefore, we started with this very simple example. You can notice it's very low frequency. We're solving the Helmholtz equation. We solve a variation of the Helmholtz equation, which we look at the scattering wave equation to avoid the point source singularity. We did that as soon as we started in 2019. And here's examples. Of course, like everybody, we compare the numerical solution with the pin solution for 2 Hertz. Not perfect. We realized early. But one thing we realized, and this is with positional encoding, which we incorporated very early as well, because we noticed it helps. I'll talk about encoding a little later. That a 2-layer network of 4 neurons in each layer, plus the position encoding, could actually, that means 96 parameters, could help us learn a function like the one we see here, a 3-dimensional function as a function of x and z, and the source location on the surface, more like a Green's function. Therefore, most of our source locations are the surface, therefore we have it as an input. And sometimes we have frequency here if we want to solve for many frequencies. Therefore, these, and with that, we ended up, this is a 3-dimensional wave field or function, and we represented it by 96 neuron parameters. Imagine this was otherwise would have required probably 10,000 grid points to represent. Therefore, we noticed that feature very early, but we noticed also that neural networks had a low frequency bias that we had to contend with. And this low frequency bias have been shown by many, and it's displayed here. If you try to fit an MLP to this multi-sign functions, added sign functions, you'll notice in the frequency spectrum of it that you end up focusing or converging the low frequency far earlier than the high frequency components of such a function. And this one, a lot of people have noticed this. Therefore, that is causing a problem. This is one of maybe the major issues we have faced since we're dealing with wave fields. And one of the solutions is something we introduced in 2021 is pinup. We thought it was a nice, catchy name. We know what pinup means in general. And this is our first play with names that included pin. Therefore, we relied on the well-known issue with low frequency bias from the authors shown here. In full waveform inversion, one of the things we do to avoid the nonlinearity, we start from low frequencies to high frequencies. Therefore, we first invert for the low frequency where nonlinearity becomes far less to avoid converging to a local minima. Slowly increase the frequency in the data and try to match those. We have a limit how low we could go because we cannot record lower than certain amount of frequencies in the field. Therefore, we use that concept here. And not only that, we borrowed also neuron splitting that was used with splitting steepest descent component. We introduced it to pin as one of the solutions to this problem. Therefore, this is what exactly we did. We took the 2 Hertz solution. After we have trained, we take this network with its weight and we split it. There's a very simple formula for splitting a neural network. We actually quadruple the size of the neural network every time we increase the frequency by double. And we go ahead and start training. And you can see on the right, starting from random initialization, both with positional encoding. With random initialization, the convergence is much slower than when you start with a 2 Hertz split larger network that is used for the 4 Hertz wave field. And we continued doing that. And you could see the quadrupling every time of the network size. And we ended up getting to 32 Hertz. Look at how complex the function looks like here. And here's the pin solution. 2 layers. We still with 2 layers. There's no splitting in the number of layers. But we gone from the 4 to the 8, to the 16, to the, okay, my math is not at that level, but we ended up here with 1024, 1024, and look at the residuals, barely, even better than the 2 Hertz. And that's one of the things we have noticed and we liked with this approach. Of course, yes.
Tariq, can you explain a little more again, the method? From that, did we lose him?
Yes, yes, George. We lost him.
Okay, I thought he didn't want to answer the question. Let's see if he can come back. Umer, if you can text him, please. Maybe you can stop it.
Sure, George, I'll do that.
Oh,
He will reconnect.
yeah.
Mario is right. Italy is not so reliable.
Yeah, he's never been, sadly. Probably it's due to the storm back there.
Ah,
All the cities in the north are flooding.
yeah, flooding.
He's back.
Hello,
Okay,
Professor.
okay, sorry. I warned you guys. This is sorry for that.
Yeah, no problem.
Okay,
Tariq,
yeah,
Tariq, I asked if you could, when you disconnected, I asked if you could explain a little better what's going on actually, because
Yes.
like in an algorithmic sense, what is the algorithm there? You split the neuron, but yeah, can you explain for everybody? So you can explain
okay.
again.
Oh, yes, no problem. No problem. Let me do that. Let me share again and get it up. Okay. Here we go. Okay.
18.
Yes. The idea here is when you finish training the 2 Hertz network, there is a simple formula to make sure that when you split the neurons, meaning let's say we split it each neuron to 4 neurons, you divide the weights to 4 of the previous layer. I could get you the exact formula of how to split to get the concept here is the prediction will be exactly the same at the end of the day. Therefore, you have not changed the prediction. The weights will give you almost the same type of prediction, but it becomes the initial weights for the 4 Hertz application. Whatever we ended up with 2 Hertz, we actually have this formula of for the bias. There's a different formula than the weights. The weights are divided by 4 if you are splitting or offspringing each neuron by 4, and weights, and for the bias it is divided over 2, I think, but I have to get you exact numbers. It's been a while since, but we have a publication. I could share it.
Say you start with the 2 hertz, you train
Yes.
all the way to convergence, right?
Yes,
So you get the weights. Then you say, I'm going to tackle the 4 hertz range.
exactly.
And then by doing that, you expand the network, only the width, not the depth.
Yes, only the width.
And
And
when you go to 1024, you have basically a pretty wide network.
yes, by the time we got to 32 hertz, it was 2 layers, 1028 neurons per layer.
Okay, got it. Thank you.
And you could do this with different configuration. It's not limited, but we did our tests with the 2 layers, and it worked out fine in that case. And amazingly, this is the one we surprised with, is the accuracy we got when we got to this level. And it is considered efficient because when we train the 2 hertz, it's very cheap. You have a very small network of 4 neurons per layer. Their training is almost instant, very fast. And as we get later and later, it will be costlier and costlier. But you could see that the improvement, because of the difference between random initialization and what you get from starting from a neuron that has been splitted, is a big difference. And we also show in the paper what happens if we decide to keep the neural network, not split it. And of course, when you keep the neural network and go to 4 hertz, which is more like transfer learning, you'll notice that its fit to 4 hertz becomes more impossible because 4 hertz, then 8 hertz require a bigger network. Okay, let me, okay. Therefore, one of the beauty of this implementation of fitting or storing the velocity model inside a neural network to predict travel time, and here is an example of a travel time for a source located somewhere in California, is that you could invert the travel time to get the velocity model. And here is a comparison between the true velocity model on the left, 24-kilometer depth, this is a slice, with the true one, and they are very close. Therefore, we stored a huge gridded model that we have a hard time putting in a hard disk inside this neural network, and it predicted really well. I'll show how this is manifests itself in many applications down the line. And of course, we tested its interpolation properties. Therefore, we trained it for the US array. And despite that we trained it for the US array, it interpolated beyond the US array as location for an earthquake located in Chile. And we could actually find a travel time that is way further outside the area trained. And a lot of you probably know some of that features of neural networks and PIN especially. Here's an example that we got really surprised. This is using the Eichel equation, the travel time or the wavefront mapping, geometrical shape. And here we took a slice out of what we call the Marmoussy model, a big slice shown here. This is a 3D implementation. And we ended up predicting the travel time from a source given by the star and only use information on this area, these 2 areas. This is a big gap. We didn't even use any information from this, nor velocities in the PDE, none of that. Many who are familiar with level set method know that we definitely need a marching approach. We need to go upwind. We need to start at the source and build the travel time from minimum travel time to maximum. And yet the PIN built it for us with a big gap in the middle. And if, of course, when you train it, you could apply it to any location. We filled in the areas that in the gap, and this is the travel time it gave us. There is errors, no question about it. You cannot, it's not magic, but we went and flipped this and looked at the velocity model we interpreted, and look at what we got. This is the actual velocity model, the gap. This is the part that was interpolated. and especially capturing the parts on the far away from the source is interesting to us. In spite of this big error shown here, but this is information we didn't even give to the network, yet it tried to do. And the reason it does that is because if you have a neural network that's looking at many travel time locations and comparing with the source, it does a very intelligent interpolation. And that interpolation in this really extended function given by the neural network and its many layers is doing a very good job in that arena. 50% of the velocity is missing. Okay, and we continued doing interpolation to seismic data. We use this PDE. This is what we call the slope PDE, or the wave field slope, or the plane wave destructor PDE. It just takes the derivative of a wave field laterally and with time. This is a time recorded data, and sigma is the slope. Therefore, what we do is we have a gap in the data, and we train two networks to fit both the data, and this PDE in PIN. And we invert for both the slope, a network for the slope and network for the data. And when we do that, it fills the gap perfectly. Almost perfectly. There is some errors, but very minor one. We did it even on real data, and here how well you could utilize PIN to fit the gapped area. This is a close-up of what you see here, and you could see many events. It's not perfect, but it did a good job, and it's because unlike many that use least square fitting and use other approaches to try to fill in such a gap, we used a PDE within PIN, and it did a good job. Therefore, this is one of that, but this is actually the work of Francisco Berdinoli in our group. Okay, another application, I'm going to show some examples, is imaging. We try to image the Earth. We try to image the source of microseismic events for monitoring for CO2, and we use the Helmholtz equation. The imaging technique is by summing over frequency, because that's the zero time. We consider that the source ignited at zero time. Therefore, when we record it on the surface, and we do not know exactly the ignition time, therefore we actually plot many instances of time, and we pick the focused energy one. This is the concept of this imaging for microseismic. Therefore, this is the regular PIN implementation. You have the PDE loss, and you have the data loss on the right. And we train over frequency and location XZ. And we use the hard constraint in this one. We decided we had many problems with having a boundary as a separate term. Therefore, we include, and this is work up, I should have added the references of previous people that worked on applications related to including the data into the PDE. And here's the data recorded on the surface for your transform frequency domain. And we just multiplied by Z, where Z equals 0 is where the data is recorded. And now we have it all in a PDE. And you could write now a loss function for PIN that has only one single term instead of the data fitting and the boundary. But we did another trick because we're dealing with many frequencies. And this is why PIN is so nice. Because the wavelength of the waves change with frequency, and thus you have a lot of changes from going from frequency of 2 hertz to a frequency of 10 hertz, for example, or 12 hertz. We tricked the coordinate system. We scaled, we used the reference frequency. We considered that is the frequency for all our frequencies, and we just squeezed or stretched our axis. And that is exactly the same solution, but what it does, because you could control the training range for, we could, at low frequency, we could have X from 1 kilometer to 2, in high frequency from 10 to 20. We could simply trick the coordinate system. We ended up making the solution stationary in frequency. And what that does, we know that pins, when the function is not changing in one dimension, it's very easy for it to learn that, or changing slightly, smoothly. It's when it's complex changes where we have problem. Therefore, we utilize this in this application of trying to locate sources similar to the one you see here. We train 2 pins, one to fit the data, and one is for the image as a function of frequency, Z and omega. And we use both to get to satisfy this extended PDE, which includes the data. And we ended up obtaining for the Oklahoma basin. I hope I don't have to say this 10 times in a row. That will be a big test. Where they acquired data on the surface. This is easting and northing. And these are the different arms of the acquisition. Therefore, I'm going to show directly the results. And what we got is, look at the focusing of energy. We could have snapshots at different times. And we get the biggest focus where the reference location, which they used another approach, tomography, to locate it. We got it almost exactly at the same location. And this is very interesting. And of course, the error bar in their location is high. So is the focusing here, because the data is very sparse. One thing I didn't talk about here is the elephant in the room. Wow, we went into, which is cost. And this is why George invited me. Therefore, I'm going to go through this, maybe a slightly fast, but we ended up trying encoding methods to improve. The reason why we think encoding is a very interesting way to improve the speed, and we learned that from positional encoding, is because you're representing the scalar inputs with a higher dimensional vector representation, which has more imprint into our neural network. And therefore, when you update and you start back propagating and interacting the forward with the back propagated information, you get more influence of the input in trying to locate, and much easier for the wave field or for the neural network to find the solution or to find the local minima. Therefore, we started with positional encoding, and then which is also utilized in NERF, neural radiance field, which they also use multi-layer perceptrons to try to capture images or capture 3-dimensional reconstruction and so forth. Here's an example in which, when they use positional encoding, or they call it Fourier encoding in NERF, and some of it, ours is fixed, the positional encoding. There is positional encoding or Fourier encoding that have learned parameters. You could see the improvements here. Look at the resolution of the picture, missing the eyes, much better. You could see the eyes, you could see, and all these pictures. This is an MRI, and you could see much higher resolution obtained by the MLP. Therefore, we could borrow a lot from NERF. We ended up borrow something very interesting that is called hash encoding, and specifically multi-resolution hash encoding. The idea is not hard. You have an input location in which you want to train, and you have multi-resolution grid to your domain, from high resolution below to low resolution above. And for every one of these points, you floor it to get the 4 points next to it, shown here as an example. And then you use the hash function to get exactly, depending on the size of the hash table, which is the most important parameter, you actually place the information in one of these columns here, which is the hash table. And these vectors are the feature vectors that are learned. Therefore, there's part in the hash encoding where the neural network learns these hash vectors, but their placement depends on the location of these points. And that's why we are multi-resolution aware of our location in this function, because of this multi-resolution connection Therefore, this point is no longer a single point in the neural network. Points where other points, if this another X is here, it's utilizing similar points. And then there is this connection between them to create or develop the function. After we get the 4 feature vectors for these 4, we linearly interpolate. This is our big problem. And in this linear interpolation, we get a single vector representing every resolution level. We utilize 11 resolution levels usually, and that turns out to be good. Therefore, all of this process is the hash encoding. Then these 7 vectors that we have here are connected directly to the MLP to predict wave fields, to predict travel times, whatever we need. Therefore, this is the concept of utilizing this hash encoding. But there's one problem. Because of the linear interpolation, and we tried even much more advanced interpolation, still you have this discontinuity that happens on. Therefore, with this point passes this border here. Therefore, instead of relying on these 4 points, it relies on these 4 points. The linear interpolation utilized admits a discontinuity in the derivative. In their applications, in NERF, they do not need the derivatives. In PDE, we need the derivatives. We need automatic differentiation for the PDEs. And this was a problem for us. Therefore, we ended up testing this. And here is an example of taking the first and second order derivatives. And you could see that it is highly unstable because of this problem. It comes from the many different layers. However, as we increase the table of the hash encoding table length, it reduces. But you increase it, you increase the number of parameters that the neural network has to learn as well. We decided to do finite difference instead of utilizing automatic differentiation. And here is the result of finite difference. Still, we had a problem because with a table of 4, you have something called collision. That means as we try to locate for these 4 from the function where it's located from the hash function or what they call the remainder of the division, they might fall at the same location, which is not a problem for implementations in NERF, but it's a problem when you have derivatives because you have non-uniqueness. And both of these problems created an issue. We notice, at least with finite difference, when we go to a table that is at least 10, it is fine. Therefore, we started testing this. We tested this with Berger's equation, with all the boundary conditions and the initial conditions. And here is some of the results from it. And you could see the convergence is much faster than the vanilla pin. In our case, we used the original vanilla pin with the atom optimizer. Some people used with LBFGS, which gives worse results. We used it with the pin, but no positional encoding here. And you could see that both the PDE loss and the fit to the numerical solution, this is the loss in the solution, is much better with hash encoding. A tenfold decrease in the amount of training needed. We tried it on the Helmholtz equation with, this has an analytical solution with this force function, which given by sinusoidals as well as the boundary conditions. And we got this result. And you could see again, both the PDE loss and the solution loss converge really fast, tenfold drop almost. Navier-Stokes equation. And you could see the solution on the right. And both again converge really fast with the hash encoding. And we did one more. Here's numbers of the cost. And you could see it's a tenfold decrease compared to, and we try to be fair. Therefore, the networks we use for the pin, we added more neurons, so it equalized the learned parameters needed for the hash encoding. And that's why you see the number of parameter size is very similar between them. Otherwise, if we use the same neuron size, we would have more parameters in the hash encoding because the hash vectors are learned as well as parameters. And here we tried it to our problems. The problem with what we do, we don't have boundary conditions. We deal with the Earth. We deal with an open-ended Earth. And we have a source function. We could put a boundary on the surface of the Earth, but that's it. And therefore, our constraining the solution is always a problem. But nevertheless, here's the results of 3. This is the original pin. This is the positional encoding in blue, what we had previously. The hash encoding is given, I'm not good with colors, in black. Okay, I think I'm running out of time. I had one more topic on our latest stuff on latent pin, but I have to, I think, jump that. Otherwise, I will not have a chance to receive any questions. But this was, let me at least advertise this. We call this latent pin. We just shared it in archive. And the simple idea is we do not only train with input coordinates, we also train with input latent space. And this latent space that come from the autoencoder training for example, the PDE parameters, like velocity in our case for the iconal equation. This training that we train, and this is the first training, a decoder to learn a latent space vector of 96, is input to the pin. The reason is we want the pin to generalize, give us a solution not only for a single PDE or single velocity model, for many velocity models by just simple, not like meta PDE or meta learning PDE in which they do that, but you have to do a fine-tuning training after. No additional training required here. And we tested with Gaussian random field velocity models, and this is the travel time solution for unseen in the training. Therefore, we trained the autoencoder with probably like 1,000 samples. We trained the pin only with like 50. Only that's needed, latent space. And this is the predictions, as you could see here. And here is the velocities, the original. Here's the ones that come output from the travel time. And here is the training for, we tried it on Gaussian random fields, on the mechanical minst, and from real C model data. But this is the interesting one. Here is the result of training random, the one in blue. Transfer learning, when we take a trained one and we move it to a new data, actually converges faster. But here's our instant. Of course, we did pre-training on the random, but now we could get results instant, and it's even better than the other 2 methods, almost. On a new model, it was not trained. Therefore, we call this actually a generative pin. I don't know if we're fair. We tested on the Marmoussi, which is very different than the random generation model. Okay, I should stop. And this is my conclusion. And I thank you guys. If there's time, I'll tell you a story of this, which is maybe later.
Sure, Professor,
okay.
Sure. Yeah, we have time. Yeah.
Okay. Yeah, I know with the cutoff, I had this fixed on the hour, but we started a little late, and we also had that interruption, which is my fault. Okay.
I think Kamal has the question.
Yeah, hi, it's Kamal from Brown. It's a nice talk.
Thank
I have
you.
a small query. So I have a source.
Francis, can you
and
please turn off? Mute?
Yeah, sorry, it's just
If you can mute your, yeah, okay, go ahead, Kamal.
Yeah, so there is source and a receiver. So if I am having some human activity, say like some underground train is moving, so will it corrupt my results, or how to deal with that?
If you do what? You're talking about what part?
In some inverse problem, if I'm trying to do it, so if
Yes.
I have a source and a receiver, so in
Yes.
between, if some train is moving the same time or some human activities are going on,
Yeah.
so will it able to predict or it will corrupt the result?
If you mean like noise because of human
Yes.
activity?
Yes, exactly.
Yes, of course, noise has its influence. We also, one of the things we have done is study the uncertainty in the weights of pins. This is in a study that Umair was involved with. We call it hypopin pin, but we were looking at how much pin weights are affected by noise, by other features that could happen. And yes, there is some sensitivity, and we have to take that in consideration. Therefore, that could be a problem, yes.
My doubt is like, will it predict the moving train or it will corrupt the results?
A moving train.
Yeah, so it can predict like the activity, or it will.
No, I'm not sure what is the scope, because we also have DAS networks that try to listen to moving trains, and it's seismic, it waves, and we haven't as a group looked at it, but it's a very interesting application. Therefore, if you're talking about that as a source of energy that we need to find the solution, I'm not sure if that is the question.
Like we have a seismic source. At the same time, some activities are going on. So the model will predict the activity, or it will give a wrong result.
The other activities will act as noise if it has signatures in the data. The more you put a priori information, the more it will focus on what you are looking for. Therefore, if you constrain the model to be in a certain shape, these awkward activities that show up in your data will not be taken into consideration. If you allow to fit anything, yes, you have a problem. This is where a priori information and constraints on the model space is very important to make sure that it does not fit many types of noise that could, and I agree with you, this could affect the results, but the additional constraints, and we're going to have some new things coming out in pins related to that, is one solution. Yeah.
And like secondly, like when you are doing the discretization, how large is the domain and the mesh sizes?
The mesh size for the pin.
Yes.
We typically do not use a fixed mesh. We use random. Most of our application is based on random. We just a collocation of points from the domain. And if you're talking about the hash encoding, it's the same thing. It's random. However, we have this mesh just for the hash component. Therefore, this mesh is just there to incorporate the hash. Otherwise, these points that are picked are random points for the training. But this is a multi-resolution, what do you call it? It's like a multi-resolution awareness mapping. It's trying to use the different resolutions of connecting the points. Now, notice that I have this point here, and it's sharing these two. And if we have a point here, it will share these two as well. And they're learned vector feature. And it means at different resolution, information here are sharing at a lower and lower resolution and higher sharing information as they build the solution. And let me be fair, there's another group that done without hash encoding, data multi-resolution. It's called Pixel. I could share the paper, and they get also good results. But in their case, be aware, in their case, they compare their pin with the vanilla pin, not with Atom Optimizer. They compare it with an LBFGS. Because with this multi-resolution, the LBFGS does really well. But we intentionally fixed our comparison to Atom.
Thank you.
Okay.
Hello. Hi, thank you for the nice presentation.
Thank you.
This is Socrates from Brown. I really like the idea with the network splitting the neurons. And I assume that there's a similar formula for depth-wise, or is there?
We have not thought about it or have used it. This one, of course, was utilized in another paper, but wasn't utilized in PIN. Let me go back so you could see the reference in which it was utilized. And we thought it was because this whole idea came from us dealing all the time with going from low frequency to high in full waveform inversion. And Umair knows that. It's very popular in our field, this concept. Therefore, when this came up, the neuron splitting, we said, this is perfect. This is like when we regrid our velocity model from coarse grid to fine grid as we go from low frequency to high. And the same thing holds here. I'm probably making everybody dizzy trying to find, yes, here it is. Therefore, the only splitting we did is the width. And it comes from the paper, where is that paper? This paper here. Splitting steepest descent for growing neuron architectures. I could also share our paper. It's available as well. And it explains in detail how the splitting is done. And it's also in this paper as well.
Sure, thank you. And I have one more question regarding the finite difference scheme that you're using.
Yes.
So when you're trying to apply finite difference schemes instead of the automatic differentiation, you might notice that you get faster convergence, at least for the loss, the training loss of the network, because of the inherent stability of the finite difference of the differentiation, especially if you use central differences schemes. But if you test the L2 norm, you might see the opposite result. So, for example, if you go in the Berger's result, is it possible?
Yes.
Yeah, here. So this here, just to make sure we're seeing the training losses on the graphs, right? Not the L2.
Yes, you're seeing the loss. There's no training or testing.
So the training loss with finite difference is because you decouple basically the differentiation from the network, might actually have this behavior. But when you test the L2 loss, so you see in the result you have for the pin, at the discontinuity you have these lines.
Yes, yes.
So if you go and check the L2 loss here, I'm pretty sure that it will be quite higher than the vanilla pin, because I've tried it myself and I've seen similar problems with the discontinuity, especially. So my suggestion would be to test the L2 loss instead of the training here.
The L2 loss, to use the L2 loss.
The relative L2.
The relative L2 loss. And that would help the finite difference.
So when you make the prediction after you train the network, you just compare against the exact solution with the L2 norm, the L2 loss, because the training loss might give you
L2 norm.
L2 norm. Okay. And you're recommending that we use another norm?
No, basically here you're showing the training loss. So the training loss is based on the scheme that you're using for the finite difference, but that doesn't necessarily correlate to the actual accuracy.
We're showing both. We're showing the accuracy as well. Therefore, you're seeing both here. You see the lower curve here is the fitting of the numerical solution in L2.
Yeah, but that's compared to the finite difference scheme that you're using. So
no,
depending on what scheme.
We're only using finite difference. What you're seeing here is finite difference versus the numerical solution. And here is the vanilla loss, the vanilla pin.
Yeah. No, I completely understand. I'm just saying that it's two different things. So the training loss is quite different than the L2 norm loss, the L2 norm difference, basically, because in the training you might see a behavior like this, where you have very fast convergence, but this only gives you the convergence of the finite difference scheme that you're using. It doesn't necessarily tell you the difference you have from the exact solution. And as you can see in your figures, the L2 norm, the actual difference from the exact solution should be quite higher than the vanilla, because you have this
Socrates, the green curve, the solution accuracy. The solution accuracy should be with the reference solution.
Yeah.
The green curve. Look at the green curve.
Yeah, this is with the reference solution. Therefore, we haven't shown here the pin vanilla solution. Otherwise, it should be worse because the loss is higher. No, it's not higher. It's here. This is the final loss at very large epochs. This is the vanilla pin. But I agree with you. This is a very good point. This is courtesy of the finite difference. Of course, we definitely want to do automatic differentiation because we know its accuracy and it's based on both symbolic as well as numerical, very accurate, not second order or any.
Tariq, I think Socrates and I think there's something wrong with this plot because the blue curve. I don't know, you said you cannot distinguish colors, but the blue curve is a training PD loss for pin and hash.
Yeah.
And that's higher, that's larger than the error. So that doesn't make sense.
Oh, no, this is the PDE loss for the training. Of course, the units of the PDE is not the same as the units of the wave field. Or not the wave field of the solution field here. Therefore, the solution field here will have different scale than the PDE. This is Berger's equation. Therefore,
allow me. How could the solution, the error, how could the error be smaller than the loss? Usually, the error is the square root of the loss.
I think what's going on here is that the reference solution he's using is the finite difference solution. So they are bounded by the accuracy of the finite solution. That's
what Socrates is objecting to.
And then it can happen because if the reference solution was the exact solution, then you cannot go lower. But here,
cannot be.
What I'm trying to say is that. Because I ran the exact same case.
The PDE loss is this total loss, this loss plus all the boundary losses. That's the PDE loss.
So the training loss, while you're training, you're plotting the training. Okay, but what I'm saying is that it's true that in the training you might see the loss go really fast, really low. But that doesn't necessarily mean that you're getting to an accurate solution with respect to the exact solution. As you see on your right graph, on your right plot, figures, there is a problem with the discontinuity because of the finite difference. So all I'm trying to say is that the finite difference is a fast scheme for the differentiation, and it's really stable because of its numerical theory, but it doesn't necessarily
give you
better accuracy.
Yeah, we commit a crime and accuracy crime.
So you have to test the relative L2 norm at the end just to make sure that.
Or what you can also do is like take a very fine numerical solution, like the finite differences scheme could be very high resolution, so that your accuracy of the finite difference will be like 10 to the minus 7, and then the pin could be probably compared to that. But if the accuracy of the finite difference is 10 to the minus 2, like most schemes, then you will see gaps like that you don't really want.
Yeah, no, I agree. This is you're absolutely right. This is courtesy of the finite. This is the finite difference fitting, which is an approximation to the PDE solution, this is the numerical solution. It doesn't have that issue, as you could see here. If you notice, it does not have the issue because we do it at a very fine grid, and the difference here, yes, you will end up saying it did not. Yes, it's not zero. The difference. There is errors here, and we're not at zero. Therefore, when we take the L2 norm difference between this and this, it comes down to here, but it's not perfect because of the finite difference.
So if you plot the corresponding accuracy for the vanilla pin, I I think that it will be lower than the green line because you won't have
This is the same. This is the vanilla pin, but the vanilla pin is also is finite difference here. We're comparing apples with apples in this.
Okay. I see.
Yeah. I probably didn't mention this component, but we're comparing. That's why you see almost similar level of accuracy.
I see. And do you remember what type of scheme you used for the finite difference? Was it central? Was it Kronecker-Nicholson?
Central difference, just depending. Of course, in this one, you have a very huge discontinuity, and you could see almost similar to like a Gibbs phenomena type of fitting. But I cannot remember exact number of the width. This is Xinhuan's work, and I need to get it from him, exact size of the finite difference. But it's a central difference.
And just one final question, sorry. Did you use scattered points to calculate the finite difference derivatives on those points, or did you use a grid for the collocation points?
No, this one. No, for the finite difference, yes, a grid. Okay,
maybe these inaccuracies you have in this continuity could be further improved if you used an odd number of grid points on the y direction.
Yeah.
Just a suggestion.
There's absolutely right. There's a very interesting paper, and we're guilty of not really following up on this, that calculates, even if you have a random number of points, will calculate for you a highly dependent points in 2D, for example, a very good accuracy derivative or second derivative based on a form of integration. And we wanted to try it. We haven't done it yet. We got distracted, but that might help the finite difference implementation on non-regular grid.
Okay, thank you.
But definitely share with me any help our work, and we'll acknowledge that or point me to. We have been guilty of not looking as much into work.
No, it was a very nice presentation. Thank you for the clarifications.
Thanks.
Any other question?
I have a last question. I'm Somdata from Brown. And I wanted to ask you regarding the neuronal splitting that you showed.
Yes.
The graph that you had on the right-hand side.
Okay.
Could we go back to that slide, please?
Oh. Yeah, here it is.
Yeah. So I just wanted to know the results that we have for the random initialization. The network size for that is same as what happens finally for after the neuronal splitting. So it's 1024 cross 1024.
Not for this. The 1024 is when we ended up at 32 hertz. We started with 4 for the 2 hertz. This one is 16, 2 layers, each layer 16. And we trained from random initialization, positional encoding, and this is the blue one here. And we started from the neuron splitting that learned from the 2 hertz. And this is the, I'm not good with colors, the green one here.
Okay. Yeah, thank you.
This is at 4 hertz, and 4 hertz we're at 16. After 16, you multiply by 4. What is that? Okay. 64, right?
So both of them are 2 layers of 16 neurons each for the
4 hertz.
Okay, thank you.
Can I take the last question?
Go ahead, Jack.
So hash encoding is really interesting. So I wanted to know if there's limitations, because we have this Korean group that show us a factor of, with a separable pin, a factor of 100 speed up in 3D problems. And I was wondering if we would add another factor, which seems to be like a factor of 10, what you show us, Tariq. And because any limitations, basically the question is any limitations, or it could be used for separable pins or all kind of pins. all the alphabet of pins. We can use, on top of that, we can do hash encoding. Is there any limitation?
Okay. First, you have to share with me this 100 speed up is for 3D or
Yeah, for 3D problems. Yeah, 3D problems.
okay. And what do they use? It's
the separable pin is basically you have multiple pins, multiple networks for each dimension. Instead of like x1, x2, x3, you have a tensor product of functions in x1, x2, and x3.
okay.
And we have implement ourselves. We know that it's a factor of 2 orders of magnitude, let's say. But I was wondering, on top of that, if you can use hash encoding. I don't know if Raj is listening. Maybe he can also tell us.
Yeah, I'm going to look at the separable pins, but for the hash encoding, we have, I mentioned the major weakness is this derivative, which we're trying to solve. We're currently trying to find ways. The source of it is this linear interpolation that we do here. And we could do better than linear interpolation. We already tried it. The problem is you still have a form of discontinuity. By the time this point goes from these 4 as a linear interpolation from these 4 to these 4, you created an artificial discontinuity in your function as it relates to the point.
Can you use kriging, Tariq, and local kriging, and therefore you can smooth out and then with overlaps?
We're trying. We don't want to compromise the speed because the lookup for the hash encoding is almost instant. And there's many features that are very fast in the hash encoding that we want to keep, but we're definitely looking at that component.
Yeah, so I can add upon hash encoding for the separable pin. So as long as your input is in the structure like grid format, you can use the separable pin for that input actually. So because it creates the output on a lattice with a tensor product. So your input has to be on the grid, like not random.
Which will also help the difference.
Yes,
Okay,
yeah, exactly. Yeah. Also, Professor Alkhalifa, I just had one question on this because you mentioned there is a collision in the hash encoding. So, but usually the hash data structure has a chaining, so you avoid collision. So why hash? Because usually when we create hash data structure, we have a chaining to just check whether there is a data or not. So then we move pointers. So why there is a collision for this kind of setup?
No, the collision comes from, it depends on your hash table. Imagine, for example, the hash table size here is let's say there's 10, for example.
Yes.
Then you have all of these points that map to different locations here.
Yes.
There's no problem if certain points map to the same location, if they are not interacting with the same point within the 4.
Okay.
But if they are interacting with the same point 4, but it's not an issue in NERF, such collisions is handled later by the neural network. It will recognize, it will heal such collisions. It will not be affected that much. It's an issue when we take the derivatives.
Okay, that makes sense. Yeah. Thank you very much.
But it's related to this implementation, yes.
Okay.
But good point.
Okay, thanks.
Tariq, thank you very much. Your talk generated a lot of interest, and my suggestion is whenever your schedule allows it, you can visit us here. When the weather is too hot in Saudi Arabia, you can take a break from the and visit us. And anytime you have an open invitation. A great talk.
Thank you very much, George. I really enjoyed it and enjoyed your visit and enjoyed the interaction and discussions we had. Thanks for inviting me. And could I get I think my student that is working on this would love the comments. Can I get the recording?
Yeah, the recording will be on YouTube, and some data will send tonight the recording also by email, but everything is on YouTube. So all the good and the bad things that we talked about will be on YouTube.
Okay, good. Okay, I hope it's all good. Okay. Thank you very much.
Okay.
Yeah, thank you. Thank you, Professor, for the presentation.
Thanks, everybody.
Yeah. All right, now we move to our second talk. Our second talk is given by Xinyu Liu from Purdue University. Xinyu is currently a PhD student in mathematics in Purdue University, advised by Professor Jie Shen. His research interests lie in the field of scientific computing, data science, and optimization algorithm. Oh, hi, Xinyu, I can see you. You may want to start. Can you try sharing your screen? Right, yeah, we can see them. No, you muted yourself. You have
okay. Thank you. Thanks for Zoran's introduction. I'd like to thank Professor Kaniadakis for inviting me to speak today. I'm truly honored to be here. And today, I will be talking about a new SAV-based minimization algorithm. It's a joint work with my advisor, Jie Shen, and also Professor Xiangxun Zhang from Purdue. In my talk, I will first give the motivation of scalar auxiliary variable approach, and then move to the SAV, relaxed SAV and its adaptive variant. And finally, some numerical results will be given, not only some benchmark problems, but also some machine learning related problems. My hope is that by the end of this talk, you guys can have a better understanding of our new algorithm. And so without further ado, just let's get started. So consider a typical minimization, without any constraint, just try to minimize the f, the function f. The first thing come to my mind is the gradient descent method. This method can be reformulated as a gradient flow as equation 1 with a constant, or you can vary step size eta k, which is commonly referred to as the so-called learning rate. We can say that in this line, this equation 1 utilizes the information from the gradients. So we can consider some gradient based methods such as stochastic gradient descent, Adam, Nestrov accelerated gradients, which are widely used and proven efficient in practice applications. However, there are several potential disadvantages for this gradient-based algorithms. First, the step size, right? Or the learning rate is really hard to choose. Usually, we must give a learning rate schedule to train a really good enough model instead of a constant step size. Another thing is when we try to train the neural network, the gradient may go really large due to the backpropagation. This may require the step size be very small, otherwise the model will blow up. Also, when the data set is really large, the cost of the full gradient computation is not affordable. When we use stochastic gradient descent, just one training data each iteration, or mini batch, right, which is just a subset of the whole data set. In this way, some noise may be introduced since we don't have the full information about the gradients. So to solve these problems, we consider the SAV approach, which can keep the modified energy decreasing. Before it comes to the SAV part, we first split the function as two parts, a linear one and a nonlinear one. This splitting doesn't makes any difference under, the continuous system. However, when it goes to the discretization or in practice, the optimization, it can become a little bit different. Inspired by the SAV approach, we first introduced a scalar variable R here, defined by the square roots of f and plus a constant. The constant here is trying to keep the f be positive, the sum be positive, so you can do the square root. And then as expand to the equation 2, we can rewrite the equation become a system as 3 here. My personal view for this system is the first line utilize the information of gradient. You can consider it's okay. It's a gradient driven dynamic or path. And the second line utilize the energy dissipation law in the gradient flow. So it's also the reason why we rewrite it as a gradient flow. So it's an ideal dynamic that energy will always be decreasing because its gradient flow has energy dissipation law, but it's not always true in optimization. And given this system, we can obtain a simple SAV scheme after like discretization. Notice that in this way, like when the parameter theta converges to, like, for example, theta star, the system will lead to the gradient of theta star is 0. And it's a solution of our original, like the gradient of theta goes to 0. So in another word, like in this splitting way or in this simple SAV scheme, won't create any other new local minimum. This is one remark I want to give here. And then, like, record gradient flow in the equation 1. Like we can replace the gradient f.
Can I ask a question?
Oh, sure. Go ahead.
Can you go back? So this scheme relies only on the gradients of f, but with respect to the parameters, right? With respect to theta k.
Right.
But not. But you're saying that you don't take the gradient of L with respect to theta k.
Yeah.
Because nowhere you have gradients of L here.
Yeah, right. L is just a linear operator. You can like preset it.
L is the PD. L is the loss, isn't it?
Sorry, L. You say L be loss or something?
LU equals F or something like that, right?
Right.
What is the problem you're solving? L on U equals F.
For example, like L can be Laplacian smoothing. It can be a smoothing operator, like it. So the problem we are trying to solve is still be to minimize F. It's like the L is a thing, like is just a positive linear operator. You try to add 1 and minus 1. It's actually is 0. It's nothing.
Can you go back? Can you please go back one? I want to see what is the minimization problem we're solving.
Yeah, just this one.
Okay, so you minimize F. Okay, so I'm confused because if you're still taking the gradients in your scheme, you still take gradients with respect to F.
Right. I think so. You can say the first line, like F theta, can be rewritten like I plus 1, positive 1, and minus 1, like the inner product. And if I take, because here L is a linear operator, so if I take the gradient of the right hand side, it will give me like the second line right here, theta t plus L theta plus. Yeah, okay. Does this make sense? Yeah.
Yeah, but I'm just trying to see in the next, on the next slide, you're still taking gradients of F everywhere, and the only thing that I see is new is that you're introducing this smoothing operator. I think that's what you want to have L as a smoothing, right?
Right.
So you brought in L at 2 successive iterations, theta k and plus 1 minus theta k, and okay, but there's still a lot of okay, fine, thank you. Just continue.
Hey, Xinyu, just one question. What is delta t here in equation 4?
Oh, you mean what is theta k for? Like is
delta t. Yeah, delta t. In equation 4,
actually, you can rephrase it is like the step size or the learn rate you use. Like, for example, you do a minimization problem, right? Like you do the gradient descent, you're gonna be how like yeah, okay, you got it. Okay, cool.
But it's the learning rate, right? It's one over the learning rate.
It's just the learning rate. Yeah, but because we do the like gradient flow, so we use delta t. Like just try to connect it with.
Yeah. Okay.
Okay, cool. Okay, like recall the gradient flow, like equation 1 is like energy dissipation in this science, that like the derivative of F is gonna be equal to negative and the square or the norm, a square of the norm of theta t. So, and also SAV exactly is the same thing, right? Like, so again, we can think SAV gives a dynamic from the energy dissipation. And for the gradient descent, it's just have a dynamic from gradients. So there are going to be two dynamic. One is like the gradient descent dynamic. One is from the energy dissipation dynamic. But in continuous, it's fine. Like we can rewrite it in this way, because in continuous, R over the square root of F plus C is always going to be 1. But after discretization, it won't always be true, for the original energy. So for implementation, we can rewrite the scheme 4 as following. We can consider the colored ratio, R over the square root F is a adaptive scalar to adjust the step size or the linear rate 30 here. Because A inverse is just given by the splitting operation, but it doesn't change because we can also do the splitting to the gradient descent. It's not created by the SAV. The SAV is give a adaptive scalar to adjust this step size. And for example, if the gradient is really large, then we will obtain a really small RK plus 1. And then the ratio going to be really small. So even though we have a really large linear rate 30, we can still be safe, right? Then we can obtain the unconditionally energy stable theorem for the simple SAV scheme, in the sense that for the modified energy here, I want to comment here, for the true or original energy, we don't have this theorem. It's only for the modified energy, because it's come from the energy dissipation law. So we will have the unconditionally stable. But in practice, sometimes it it can be useless, because there can be a certain distance between the true energy and the modified one. And also we can have a standard convergency analysis. So for the SAV, assume F is convex and gradient F is Lipschitz continuous, we can have this following theorem. Like I said, it's really natural to ask, was the ratio always close to 1? Because if this ratio is close to 1, we are safe, right? We can keep going, and the true energy and the modified energy are close to each other. We can consider it as we come close to the gradient descent. But the answer is no. If the ratio is really small, the parameter may not update anymore, because if the ratio is small, we can consider, okay, the linear rate is adjusted as a really small linear rate, so it will be updated really slowly. So sometimes when the R, the SAV become really small, the first thing we come to mind, at least for me, okay, we can restart, right? Why not? We can restart at each iteration. But this restart scheme will not keep the energy dimension. So we consider, would there be a balance between the modified energy and the true energy? So here the relaxed SAV comes. So for example, for the small linear rate or small step size, we can say, okay, these two dynamics are very close to each other. I can say almost same to each other. But for the large step size or large linear rates, there'll be a gap here, right? The original dynamic or the gradient driven dynamic are far away from the dissipation law. So here is okay, we hope we have a relaxation step to push the SAV dynamic or the this energy dissipation dynamic go back to the original one. So So the relaxation step has been highlighted here. Like, okay, we need a relaxation parameter C, like to balance these two terms. The first term is obtained from the SAV, and like it's the second dynamic, right? And the second term is like the first dynamic, like the gradient informed dynamic. So the side V is saying that, okay, I don't need the energy dissipation holds exactly, right? Like, so here is not like the negative theta t square anymore. I just need to like the modified energy to keep decreasing. In another word, like this scheme gives up like how much the energy decrease, but to obtain this space, like to push the modified energy back or close to the true energy. So, and also like this artificial term like eta, we want to, okay, you can push back as much as you can. So we choose like 0.99 here. And also, this is only one choice of C, which means, okay, there can be another choice, like there can be another like scheme, like to decide the value of C. It just gives one way to select the C. And here I want to remark here, like 0 here is like the worst case we don't want, right? Because if it's the best case we want, like if it's 0, so the SAV is exactly the true energy here, right? Like RK plus 1 is equal, it's gonna be equal to the square root of F theta kji plus C here. It means, okay, I choose the SAV dynamic, go back to the true dynamic. And then since, okay, we still have the unconditional energy stable in the sense, okay, it keeps decreasing, but I don't know like how much it decrease, but it can still keep like energy stable here for the RSAV. And another like advantage, like the RSAV method, like is different to the other gradient descent method, is like we utilize the information from the loss or the so-called energy here, because we can say like from the gradient based method, they don't utilize the F here, even though they do have the F, but they don't use it, right? And SAV utilize it, so we have like the energy dissipation here, and we can use like this indicator, like so the first one, like the numerator is the RK is the second dynamic, and the denominator is true energy. If like the ratio is very small, it tells us what? It tells, okay, you are far away from the true dynamic, you need to go back. Which means, okay, you need to change the step size to a small one rather than keep using a large step size, because the large step size has already caused this two dynamic be like far away from each other. So we can preset like a gamma here, like to control like the distance between the modified energy and a true energy. And then like it gives the whole like adaptive relaxed SAV scheme here. So what we need is, okay, you have an initial step size, right? Like you can choose this large or small. It depends. It just choose one you like. It's because the SAV can enlarge the range of like parameter selection. And then like, okay, you need to tell this scheme that's a lower bound of the step size, like a lower bound, like you don't want to, like a safeguard. For example, like if the constant step size for gradient descent can be a lower bound of as like the delta t minimum, and also the constant to guarantee the positivity of this F. And then like the linear operator, right? The positive linear operator, and like an initial parameter value, and like adaptive constant, like usually we take like 0.5 here in practice. And also the threshold for the indicator, because like this is information from the loss, right? So when we have like, so we can see here, like in the line 9, like we evaluate like the square root of f. This is the only extra cost, computation cost, than the gradient-based method. Because in gradient-based method, we just have like the JK here is equal to the gradient f. And the other thing, you can view it as a gradient descent, right? Because for the line 13, like the C, like the computation of C is just the computation of scalar, so it won't cause any like extra computation cost. So only cost here is just the evaluation of like the f here. Because sometimes the function is hard to evaluate, because for example, we have a really large data set, then like the computation of the loss will take some time. Okay, and yeah, so why we have this adaptive RSAV, like for the main reason, okay, it's unconditional dimension energy dynamic, because like, okay, it tells you ideal dynamic, and then like it not only tell you, but it can push the ideal dynamic back to the true dynamic. So it's kind of build a connection between this unconditionally stable dynamic to the our true dynamic. And also it's allow us to use a large step size, like just like I said before, like you can say, okay, if gradient is large or the step size is large, no matter which one, you can still be safe because you have the safeguard like the ratio here. And with proper splitting operator, we can have some benefits. For example, L be the Laplacian smoothing operator, but also it can be the Hessian. And I will show you some example after this slide. And also it's easy to implement and also be efficient, because we can say, okay, the only extra cost, computation cost, is the one-time evaluation of the function f here. Sorry. Okay, so we first consider a quadratic function that, okay, it's just a sum, but with different like linear coefficients. For this simple function, we can have like L to be 0, but also can have L to be a diagonal matrix where it's actually be the Hessian, right? So we can see in the table here, like even though gradient descent have the information of Hessian, right? Because in practice, we usually don't have this kind of information. First, its computation cost is really large to compute a Hessian matrix, but also like sometimes like the f is not like don't have like second order derivative. Anyway, but even though like gradient descent have this Hessian information, it still with like small learner rates or step size, it still doesn't do like good job here. So but for the SAV, like even though like we don't have like this Hessian information, we already have a really good enough like loss here. So maybe we can see the loss curve. Maybe it will be more vivid to you guys. So we can see the right one is the adaptive RSAV, and if it's L, the linear operator is 0, I mean we don't do the splitting. It's already be good enough. But if we have the Hessian, okay, it's just speed it up. So one choice of this L, it can be Hessian, right? Like the BFGS, even though we don't have Hessian, we can have some Cauchy-Newton method. Like we do the we try to generate a matrix B, like to mimic the Hessian matrix. And another choice of L, it can be like a Laplacian operator. So here like the maybe the benefit for the Laplacian operator is to like smooth the noise. Like, so we consider the gradient is add some Gaussian noise, and we can see from the table, like the gradient, even though the noise is really small, like 0.05, the gradient doesn't do a good job, and it can be diverged. But for the RSV, like, because we want to show the effect of this Laplacian operator, so we have like LB0 and another like LB the Laplacian operator, and we can say, okay, it does help a little bit to reduce noise, and also the sigma here is a parameter you can to maybe find a proper one, and during the in practice you can adjust sigma for different type of problem. So here we can say, okay, the L does reduce the noise. And then like we come to some benchmark problem, like the restriction function. It is very common to like consider as a benchmark problem in optimization. And we can say, even though like the performance of like adaptive RSAV is really close to gradient descent when the initial step size delta t is small. The reason is that like for this problem, we have for the last term it generates really a lot local minimum. So when the learning rate is small, like we don't have enough time to become a really large learning rate, so we cannot escape the local minimum. So it's just converged to the local minimum as gradient descent or Nestrov or Adam they does. And then like, but when we have initial step size as one, a really large one, it's converged to the global minimum. Like the global minimum is 0, so it's good enough results. And maybe we can see the contour. It shows us maybe better. Here we give like the same learning rate for Adam and the RSAV, because like they both have some kind of adaptive property. So we keep the Adam as same as like RSAV with the learning rate. And for the gradient descent and Nestrov, we just select the learning rates. They can have a common result, like have a good enough result, because they are both of these two algorithms are sensitive to learning rate selection. Like if you choose, for example, learning rate is 1 or 0.1, it may diverge. And we can also see the loss curve here, like thanks to the large learning rates, we can speed up the convergency. And also another benchmark problem like Rosenbrock function. Even though it looks like a linear one, but it's not, because the second term, right, here is a fourth order here. So, and like the global minimum will be at like a square repeat here. And so we choose the initial point from 0, and then we can say, okay, the adaptive RSAV still have a better performance, like even with different initial step size, because like it's an adaptive scheme. So the step size is not constant to RSAV. Yeah, it's just one remark. And we can say, okay, the laws are similar to each other with different step size. But for the other one, like we can say the Nestrov and gradient descent are really sensitive to the learning rate. They can not trained with a large learning rate here, even though like 10 to the negative 2. And Adam is a little bit weird, like for the 10 to the negative 4, but for the other two, the performance are fine. And then like we can have like the contour again, like we can say, okay, the loss curve as here, and the SAV can like due to the large learning rates, we can first have like the first iteration, the first maybe 10 iteration can goes quickly to the global minimum. And then like due to maybe the gradients become really small and we have to adjust the learning rates and to converge to the global minimum. And for the, for example, like Nestrov, it's just like kind of diverge because even though it it has been close to the local minimum, but it doesn't converge to it. It goes to another direction. And similar results for the atom. But good thing is, okay, atom can go back here, but it's take more time for the iteration. Also for the Nestrov here. And its previous is just a 2D example, and we increase the dimension like from 10 and 100 and 1000. We can see like the adaptive RSAV have like a similar performance in this test. So I think the reason is thanks to the adaptive indicator here. Like it can always tell you like what kind of learn rate will be a proper one. And then, okay, like we have some real problem, like the fifth retrieval problem.
I couldn't see where the atom was on the high dimension.
In this page or previous page?
Yeah, on this page. Where's Adam on the middle plot?
Middle plots.
Oh, that's a black one. That's
the black one is Adam. Yeah, like it's always zigzag here.
But so this is Adam with adaptive learning rate or fixed learning rate?
Like for the Adam, it's just like fixed learning rate, because like Adam doesn't utilize the information of loss function, right? So so we don't give like the similar indicator to Adam. Like we have not yet combined Adam with RSAV. It's just some work we are currently try to combine these two algorithms. Yeah. So in this test, Adam is fixed learning rates, like fixed initial learning rates, and it's always kept as a constant here.
Is it a second or is it a first order method? Just like LBFGS is second order method. Is this a first or second order?
So like for RSV here, it's not a second order algorithm here, like because it doesn't utilize the information of hashing, right? So it's still like a general version, like a robust version of gradient descent. It's not a second order.
I thought you bring in the Hessian indirectly through the L.
Oh, yeah, you can. Yeah. It's also another thing we are trying to do here. Like we can select the L to be hashing, right? Like it can utilize the hashing information, right? But for in this test, like L is just 0, if I remember correctly. Yeah, L is just 0 here. So we don't utilize any splitting technique in this test. We just want to show like the simple version, like no splitting version of adaptive RSAV is good enough for some test. Yeah.
Excuse me, can I ask a question?
Sure.
Hi, this is Panos Tinis from Pacific Northwest National Lab. So this Rosenbrock function, it doesn't matter whether it is in 2 dimensions, 10, 100, 1,000, right? I mean, the global minimum will always be AA squared.
Right.
And I mean, so I suppose that in all these cases here, you started from 0, right? 0,
right.
0, 0.
Yeah.
So it's the same thing in 2D. If you start from 0, 0, it's just close to 1, 1, right? So
right.
All I'm saying is that the initial point that you use is actually close to the global minimum, and then you find it fast. But if you go to a problem that is highly non-convex, you can get stuck in a local minimum and you won't be able to explore other minima, right?
So like maybe I can rephrase your question like okay, so in this Rosenbrock problem I start with 0 0, so it's the reason why I can convert to the true solution 1 1 1 quickly, right? And for other non-convex problem, Rehard problem, I don't have this kind of benefits, right? Is that what you mean?
Yes, because if you go back to the previous one,
this one,
if you start at a point that is not close to 1 1 and it's not in the basin of attraction of 1 1, you will never be able to cross, you know, the hill to go over to the next value. So all I'm saying is that yes, these are impressive results, but they're impressive results because you know where the global minimum is, and you take an initial point that is close to it. It's in the basin of attraction of this global minimum. At least that's what it appears to me.
Okay, so we can go back to the previous benchmark, like there's a lot like local minimum, right? So as we like the global minimum is 0 0 here in this problem, right? I start kind of far away, like here. So the thing like I'm not saying like SAV can avoid local minimum, because like if it converges, it can be a local minimum. But if you use, sometimes you use a large step size or large linear rates, it can, in the beginning, it can speed up or avoid some local minimum. It can maybe convert to a local minimum closer to the global minimum. Do I?
Okay. I mean, I understand what you do with this capital L. It's a smoothing. It's like adding a stabilizing term there. And that's why you get faster convergence. But I don't know if this faster convergence will be to the correct point. That's...
I mean, like, so in the beginning of like this slides, I say, I give a comment like, the splitting, like the smoothing operator won't create any new local minimum. So if the adaptive RSAV converge, it means, okay, it can be a local minimum, it can be a global minimum, but it won't be any new local minimum. It still be, so if you use gradient descent, it converge. So SAV can converge to that local minimum. It depends on how large the learning rate you use. But SAV won't converge to a new local minimum that's not included in original problem.
That I understand. It's just that the minimum that you converge to will not necessarily be the global one.
Yeah. It's really hard. Like for optimization, like it cannot always obtain the global minimum.
So what Adam does, because it's a stochastic method, right? It jumps around, so it can get unstuck from local minima and find something better. So do you have a stochastic version of this algorithm that maybe can allow you to jump around?
Yeah, I do. Like for the in the next example, maybe in the next two example, like there are gonna be used like mini batch, and you can see the zigzag. It's not always like grazing.
Okay. All right. Thank you.
And any other questions? Okay. Yeah, I'll continue. Like, okay, for this fifth retrieval problem, it's a problem in practice. Like, it can be a real one, but also can be a complex variable. But we can consider this gradient as just like the gradient descent. So in the complex one, which is called like Rottinger flow. And then like here, we can just think, okay, the number of n is like the size of the image. So which when the n is large, the problem is hard. And also for the mask here is like the information you have, like you can consider it. So with the M is, when the M is small, the problem is harder. So if you have a smaller M, for example, 6, it's already a really harder problem. And so array like the initial value of parameter just start with like a random initial guess, and each algorithm are keep like with same random initial guess. And we can see the performance. So here SD means the steepest descent. Like for the fixed direction, right? The best method should be the steepest descent, because it can always give you the best of learning rate, because it do the line search, right? But SAV only evaluates once. And in this problem, the steepest descent can be a fixed evaluation with like 3 evaluation in each iteration. So in this problem, but in the common, in other problem, it's not guaranteed, right? Sometimes it can be 30 or 13, right? It can cause a lot of time to evaluation the function of F. And maybe you can see the loss curve to see, okay, so for the yellow one is the best one, like the steepest descent. And for the right one is the RSAV, right? and we can see like the atom may like have the zigzag here. And then this is for the really hard problem. So even though with like 20,000 times of iteration, this 3 algorithm doesn't converge, and it will converge at about like 100,000 times of iteration. So I didn't plot it, otherwise like it's more these 2 lines will become like more like vertical. So I just plot the first like 20,000 iterations, and then like for the another problem, like the 10 mask problem, SAV also like between the gradient descent and like the blue one and the steepest descent. And if we want to do a kind of fair comparison, like the number of linear operator, this linear operator is not the L I mentioned here. It's like the evaluation of F or the evaluation of gradient F, because in this problem, this 2 operation does have like the computation cost. It's really hard to evaluate the F theta here. So we can say, okay, RSAV is kind of close to the steepest descent, and the other method is still not have do the good job here. And if we plot the step size generated by the steepest descent is the blue one, and for generated by the RSAV is the right one. Because they are not in the exact same dynamics, so they just have like, so we can say, okay, so step size from RSAV is kind of in the similar magnitude with the steepest descent. And this, because we have 2 test problems, one is for the 6 mask and another one is for the 10 mask one. And so it's a reason like we can say, okay, SAV can give a kind of good step size here, because, okay, we already have the benchmark of like steepest descent is the best step size we can have. And SAV gives a step size close to the best one. It's also one explanation why, okay, we use adaptive RSV can obtain the fast convergency. And another problem, like, okay, so the mini batch one, right? So for the recommendation system, like we want to, because like the rate matrix is can be decomposed to the user matrix and also the atom matrix. So like we can consider, okay, like it's as a matrix decomposition, but there are a lot of data here, so it's like 100,000 data sites. So I use 80% data split as the training data, and the rest will be the testing data. And we can see the performance here, Adam does do the good job here. I think Adam is the best. But for the large learning rates, okay, Adam also diverge. I mean, diverge here is doesn't the loss goes up rather than zigzag and finally converge to a certain point. But we can say, okay, adaptive RSAV do have a good result, no matter which learning rates you have. So it's, even though you have the range time, every other algorithm are diverged, but the adaptive RSAV still can survive. And maybe the loss curve can say more. Okay, my remark here is even though here I use is test data, and in this figure I showed is a training loss curve. So even though RSAV has the best training loss curve, it doesn't have the best performance on the test data. It's common in the, personally speaking, I think it's common in the machine learning problem. But we do can see, okay, SAV speeds up the this training process than the other algorithm. So in this problem, I use a mini batch rather than the full batch. So I will have even though it's kind of unconditionally energy stable, we still have the zigzag here, because since we use the mini batch, the F change at each iteration, so we cannot keep the F be the same one as a previous iteration. So it will cause the zigzag here. Another machine learning problem is, okay, the mini data set is kind of the Cypher 10 data set. It's just a benchmark for the neural network. And we can see, like I said before, I'm not saying SAV is a best algorithm or can beat other algorithm, but I want to say, okay, SAV is really robust. You can consider SAV is a robust version of gradient descent rather than a robust version of Adam, even though we compete with Adam. But we can say, okay, when learning rate is 1, the Adam just going to blow up, but it's not yet. And when learning rate is 10, and it's just blown up. So one thing we can do is that we use SAV to train as maybe in the beginning, and then switch to maybe Adam or some other algorithm you lack, with a small learning rate to how to guarantee the convergency or better convergency. And here we want to, I want to give a comment for the learning rate 0.1, even though the training loss curve for SAV is worse than Adam, but for the test results, actually they are similar to each other. The accuracy are similar to each other. It doesn't change anything. Okay, so here I want to give some concluding remarks. So one thing in our list, in this paper, we proposed a novel modified SAV approach, utilize the loss information or energy information. So we have two dynamic, right? So one dynamic is from the gradient descent, and another dynamic is from the energy dissipation. And also we give a proof for the convergence, for the convergency for the SAV-based algorithms. For example, the restart one and the the simple one, we give the convergence proof for it. I personally speaking, I think it's the main contribution of this paper. So the advantage of the SAV is it utilize the information from the loss or energy, and then build with the relaxation step, build a connection between the modified energy and the original one. And we utilize this indicator, like if you remember, it's R over square roots of F. It's like the ratio between the second dynamic over the first dynamic. We hope this ratio is close to 1, which means, okay, you are on the right path. The second dynamic is on the right path, which is close to the first dynamic. So it's truly dynamic in the operation. And also, like you don't need to bother by the parameter selection. It doesn't mean like you can randomly select a really large parameter, for example, like 10 to the 3, but it can allow you, like, if I don't want to do the learner rate schedule, I can just randomly choose a parameter from maybe 10 to the -4 to the maybe 1, maybe, yeah. It can allow the large step size. And also a large step size can accelerate the convergence rate at the beginning, not like the whole process, because we know when it goes to like convergence part, you need to really be careful for the, like, for example, small step size. But for the disadvantage, like the reason, like personally speaking, the performance of RSAV is not good is like the mini batch, how different F for the RSAV, like it helps to switch to a different one. So it cannot have like a same F here. So so if we can fix this part, we can have like a better mini batch scheme for RSAV. It should be have a better performance for the neural network problems. And also, like the fifth retrieval problem, the computation costs of energy evaluation, because sometimes for a problem really hard to evaluate the loss, you need to be careful, because if the computation cost of evaluation of F is not affordable, maybe you cannot use RSAV here, because we need evaluate F at each iteration. And for future works, like I said, okay, a better mini batch scheme. Also, like the previous question, like how can I escaping local minimum? So we try to combine, like, because we can switch another different dynamic, right? We can consider a stochastic differential equation, right? So if we consider a SD and combine it with RSAV, and the stochastic may help the RSAV to escape the local minimum. And also for the Nestrov accelerated gradient is being given in different paper to show, okay, for the NJ scheme, it can be understanding as another different dynamic. For this dynamic, we still can combine it with RSAV. And also, like the previous question, like, okay, why don't I utilize the information of hashing, right? Yeah, it's also one thing we are currently doing, like just do the second order scheme, like BFGS, to utilize to put the hashing into the L, like the splitting part. And another thing is, like worst case, I don't have gradient information. How can I do it, right? It's also another problem we are considering during this period. Yeah, this is a reference, and thanks you guys for the listening. And any questions?
Thank you, Xinyu, for the presentation. Do we have any question from Marlene?
Yeah, I have one question. Can I ask you, please?
Yeah, go ahead.
Yeah, can you go to the slide number 6? I think George already asked one question there.
Here, right?
Yeah, in this. Yeah, what is delta T here?
Delta T here is the learning rate.
Learning the step size, you mean? Okay.
Yeah, step size.
Okay.
Yeah.
Suppose in this question, it is approximation of the system number 3, 4, right? So if I choose the step size, suppose 1, assume that step size is 1. And for k equal to 1, so the first equation in the system 4 does satisfy the system number 3, the equation first, the first equation in the system number 3. Does it satisfy the system? If
it's still like, because like for the system 3, like the step size is like not a physical time, right? It's just the same way, it's a fixed time, right? So like if you want to like take the delta t in system 4 as 1, it's fine, like because you can divide 1 here, right? So there are same.
Yeah, that's what I want to say, that if I assume that delta equal to 1, delta t equal to 1, and assume for k equal to 1, and there is something missing in the first equation, I think, in the first equation of the system 4. So, and you didn't mention also rk plus 1. What is rk plus 1? We know rt equal to, you assume that rt equal to is the square root of f of t of theta plus c. So, and in the denominator that you mention f of theta k plus c and multiple by r. We know rk plus 1. We know rk equal to is rk of t equal to the square root of f of theta k, right?
So like
the doubt is about rk plus 1. What is rk plus 1?
RK plus 1, like can I understand, rephrase your question, like how can I solve this system 4? Are you asking for this?
Yeah, how to reach from the system number 3 to the
system
number 4?
We can first solve RK plus 1 rather than solve theta k plus 1. So it's the reason why I call like the ratio of RK plus 1 over like square root f theta k is like safeguard here. So if we can go to the implementation page here, we first solve RK plus 1, because you can see here for the RK plus 1, you use the information already have, right? For the RK, for the theta k, everything, gradient f of theta k and f theta k, all are the known information, right? So you can have the RK plus 1, right?
But RK, we don't have R in the main equation. We don't have R. R is like assumption afterward. It's given. How you solve it before? If you go to the main equation, we don't have R in the main equation.
Like, are you asking like how can I initialize the R? Is that your question?
Yeah. It is like assumption afterward. It comes and you assume to solve it before. If we want to solve the
if we go back to the definition of R, right? So like the way we initialize R is just that R be like for R0, right? Is the initial one is equal to gradient f theta 0 plus c. It is like
I totally understand that, but you introduce R after C. If you see that we introduce RT equal to this equation, right? The square root of f of theta plus c. But this like assumption or like afterward. But in the main equation we don't have R. So how to solve? How you assume RK in the first equation of system number 4, RK plus 1?
So we can see like in this implementation, like so I have R0, right? Then I have R1, right?
Yeah.
And then okay
anyway. Yeah, I will discuss this with you via email, and I will be glad if you could specific or explain how you reach to the system number 4 from system.
Hyman, it's fine. I think you misunderstood something. But Jerome, maybe we don't have time. So Jerome, do you have any questions?
Yeah,
Jerome?
I think what Hyman was saying is what is of the first principle to derive those equations. Let me rephrase the question of Hyman. Why do we introduce those equations? On which principles? That's my understanding of the Hyman question. Personally, okay. I have another question. It's what about the scaling? So we want to minimize f. I can always add a constant to f. I can always compose with an increasing function, and I still have the same minimizer. But now in your algorithm, if I'm not mistaken, you do not have those scalings. Does it make sense? The minimizer will remain the same, And then since you evaluate F plus C and so on, how do you can account for the fact that you should get an invariance with respect to adding a value or composing with an increasing function?
So just make sure I understand the question. Like you're asking if I add a constant here, like would it change the local minimizer? Is that your question?
No, it should change the dynamics and the speed of convergence, I believe.
Yeah, it does. Like different constants will have different like convergence dynamic. It does. So it's, but usually like if F is, for example, like or always be positive, so we usually choose the constant be 0 or a really small epsilon. Like for example, epsilon is equal to 10 to the -6. Let's say, so it won't change the dynamic too much. And for the comparison with the dynamic, we still like compute like the square root of F plus C rather than like square root of F. So you can consider.
But what about if I compose it with an increasing function? Let's say it's positive, and then I take the square of it. I still have the same minimizer. The minimizer is still the same, but the value of the function can be quite different. I mean, I observe the square. Or I could take any increasing composition of the function f. I do not change the minimizer. I change the value of f. And then in the algorithm, I didn't understand how you could be invariant with respect to that. Because this is what happened with the gradient descent. If you do the composition, let's say, of an increasing function with a convex function that has a Lipschitz gradient, then you can get back the Lipschitz constant for the composition. And so you are essentially invariant. And here you are not. Oh, are you? That's my question.
Okay. If I add a constant, at least in practice, in the example, like I don't add really large constants, and I don't think this constant can kind of like change the dynamic differently. Like we can still see the performance of like the F as what we want, like it's decreasing and goes to the kind of like local minimum or the global minimum. I don't think like maybe a really large C, like a really large constant can change this dynamic, but for the small one, I think it can be safe, like personally speaking.
Okay, thank you.
Any other question?
I have a very short question, if time allows it.
Sure.
Thank you, Xinyu, for the nice presentation. So I have this question about, I think it was slide 30. If we can go there.
Which page?
Slide 30.
13, okay.
Or one of the slides, I think. 30.
Sorry, say it again, like 30?
30.
30.
Oh, 30, sorry, okay. This one?
Yeah, okay. So for example, here you have some absolute differences that are of the order of 10 to the minus 15. And my question is, how would you deal with such small numbers and with the given precision of the machine? Are you using double precision for this?
Yeah, I use double precision. Actually, this task is run in the MATLAB because it's the default is like the double one, right? Rather than the Python, it's like the single one, right? So I do it in the double precision, right? Like the machine epsilon is 10 to the like 2 to the negative 16.
Okay, so all these results that you've showed us are running double precision, I assume.
Yeah, but for the last one, like the minis one is not. This one is not.
Okay, thank you.
All right, George, do you want to comment on something?
No, it's fine. Thank you very much.
Yeah. Thank you, Xinyu, for your presentation. So this comes to an end to our this week's current seminar. And everyone has a good weekend. See you next week. Thank you, Xinyu.
Thank you guys for listening. Thank you.
Bye.
Ooh. You like it? I like it.